All right, so 5-1-2, how high will it bounce? Rebound ratios. Many games depend on how a ball bounces. For example, if different basketballs rebounded differently, one basketball would bounce differently off a background and another would, and this could cause the basketball players to miss their shots. For this reason, manufacturers have to make balls bounciness conform to specific standards. In this lesson, you will investigate the relationship between the height from which you drop a ball to the height to which it rebounds. So listed below are the bounciness of different balls. Discuss with your team how you can measure the bounciness. Which ball listed is the bounciest? Well, I think what would make sense is to divide your rebound. Actually, I guess I should change colors here. It doesn't really matter, but what if we divide the rebound height by the drop height? And I think that would give us, so I have a calculator kind of off to the side so I don't have to bounce back and forth. So I'm going to get the rebound ratio, and on this one it rebounds about 55%. On the next one it's going to be 120 divided by 200, so this is going to rebound about 60%, 0.6. So soccer balls are apparently bouncier than tennis balls. The next one, 53.5 divided by 72. So we're going to get 74. So basketballs are bouncier than soccer balls and tennis balls. And then finally, we can see that squash balls are not very bouncy at all. So basketballs would definitely be the bounciest of these four games. So next, it says the bouncing ball. How can you determine if a ball meets expected standards? So your task, essentially in class, that would give us, as a class actually, we would have a ball, we would go out, we would bounce a ball, and we would try and organize the height that the rebound ratio went. So we would have different drop heights, and the ball would rebound, and we would see how high the ball rebounded, and we would graph it from there. So it doesn't really matter, but let's pretend that we did a ball that had a rebound ratio of 0.5. So as a matter of fact, I do have like a little rubber ball that I bought at the dollar store, and if my memory serves me right, the rebound ratio is very close to 0.5. So work with your team to model the data you collected by considering parts A through D below. So let's pretend that we had dropped the height at 200 and it had bounced to 101, because obviously it wouldn't be perfect, right? We dropped it from 100 and it went to 49. We dropped it from 50 and it went to 25. We did it from 40 and we got 21. And we did it from 20 and we got 9, or something along those lines. So again, this is just an idea of what's happened in the past, at least if my memory serves me correctly, from doing this with the ball that I bought at the dollar store. So it says, with your team, work with your team to model the data you collected by considering parts A through D below. Does the height from which you drop the ball depend on the rebound height, or is it the other way around? So which one should be the dependent variable and which one's the independent variable? Well, this one is going to be my drop height, and this one is going to be my rebound height. So I would say that the rebound height depends on the drop height, right? So this would be my independent variable, or my x, and this would be my, actually I already have it as x. So this would be my independent variable. That looks terrible. And this would be my dependent variable, right? So this is my input and this is my output. Read the math notes in this lesson. Should a graph of rebound height versus starting height be continuous or discrete? So the difference, we've already talked a little bit about continuous versus discrete. Continuous essentially means that we can connect the dots, and rebound height, and discrete means that we can't connect the dots. And we've already talked about that a little bit in 511 when we talked about the rabbit birth rates, that you can't have a partial rabbit, so we would say we couldn't do continuous, we should do discrete. Well, in this one, there's nothing stopping me from dropping this at 179.2 centimeters, and there's nothing stopping any particular rebound rate height, right? So I would definitely say that there's no reason I couldn't have a continuous graph here. So if I were to graph this data, what would it be if I dropped it at 0? Obviously, it would rebound at 0. So, if I kind of had a graph that looked like this, I think, 10 would go to 5, 20 would go to 10, 30 would go to 15. So you would sort of get this chart that looks something like this. So anyway, long story short, I would think it would be continuous because we can have a partial drop height, then we can have a partial rebound height, unlike a partial bunny where we had to go discrete. So it says graph your results on a sheet of paper. So what we'll do is we'll go over here and we'll graph this a little bit better than this. As a matter of fact, I will, I think, jump to the next thing here. We'll go 512 part B. Must open the wrong one here. So we can get a better look of what it's asking us to do. So it says graph your results, and we had already said, and by the way, we kind of already went through the continuous and discrete again, discussed it, but here you see a look at those actual math notes here. So I guess if I was smart, I would have opened up 520, and then that way we could have looked at that, but whatever. So we're going to go ahead, we're going to do a quick graph and write the equation that models our data. So this will not be perfect, but I will try to do a slightly better job. As a matter of fact, I think I'll do it up here. That way I can read CD and 21 as well. So I'll try and make a roughly straight graph. You'll remember we said that this was going to be our drop height, and we said that this was going to be our rebound height. We can, I don't know, does it make sense? Actually, now I regret putting this here at all, so I think I should put this down lower. Drop height. So let's make a scale that goes this way. We'll say, that this is 50. This is 100. Uh-oh. And this will be 200. And then what we'll do is we will get one here. And that will be our scales. So there we go. That's what we have. And we'll just plot these points. And again, you said if we dropped it at 200, it was going to come down to approximately 100. So I have a point there. If we dropped it at 150, it was going to drop to approximately 75. 100 was going to drop to approximately 50. 50 was going to drop to approximately 25. And 0 is going to be 0. So we can see here that, and we said we could make it continuous, right? So we can go ahead and go through there. So we get a line that looks something like that. Maybe not exactly perfect, but something like that. And it says write the equation of this line. Well, the equation of this line should be pretty simple, right? It just looks like it's y equals 0.5x. We can put plus 0, but we don't really need the plus 0. What is the rebound ratio for your team's ball? Ours was 0.5. How does this rebound ratio reflected in your line of best fit? Well, it's the slope. It's the change. Where is it reflected in the equation? Oh, wait. I'm sorry. Where is it? How is the rebound ratio reflected in your graph? Well, it is the slope, right? We're going up a half and over 1. That's where it shows up there. And then where is it showing in your line of best fit? It's showing in our slope. And how is it reflected in your table? Well, it would be reflected in the table. And again, we don't really have our table here anymore. But if we did, we had something that looked like, here. And it was just going to be our change in y. divided by our change in x, right? That's what slope is. Slope is called m. It's the change in y over the change in x. So we would be able to see that on any of these intervals. Even if we jumped all the way from 0 to 50, it would be 0 to 100. So we would always get 25 divided by 50, or we would get 50 divided by 100 or whatever, but we would definitely get that 0.5. All right, so that wraps up that lesson.